We have to go to the okay, good. Okay, can we restart?
Yes.
Okay. So, remember that yesterday we started to discuss experimental particle physics in terms of measurements that could be done by using the CMS experiment along the LHC accelerator, right? And for example, we mentioned this nice measurement about the alpha strong, which confirms the running with the q square, with the q, no? As predicted by the QCD. There is also a large number of prediction of the standard model that have been tested at the LHC. For example, about the top quark. And actually, TT bar pairs could be produced from the proton-proton collision, and those are the diagrams that contribute to the TT bar production. And here there is a schema of the decay chain that will give you the experimental signature. So for example, you see that the top, as you know, decays, it doesn't hadronize because it decays immediately in W and B 99.9% of the times. And then the B quark hadronize, giving a B jet, so with B mesons, while for example the W can decay in lepton and neutrino or in QQ bar. So according to the different decay chain of the top and the TT bar and the T bar, you could have a different final state. In principle, I mean, the best way to detect the top is by using final state where you have leptons, because you have less background. So the proton-proton collision is producing many jets. Okay, and so you want to discriminate your signal, in this case the top TT bar production, from the background. And the way to do that is to look for leptons, because otherwise you have so much hadronic activity that it's very hard to disentangle the signal from the background. And actually LHC is a real top factory, and you know that the top quark, it's a kind of very special quark. It has the highest mass between all the particles ever discovered. And it doesn't hadronize with respect to the others, so it decays immediately. And so it's not clear why, for example, it's so heavy with respect to the other quarks. We know that the Higgs mechanism provides you coupling to the fermions through the mass. Okay, but we don't know exactly why the top is so much heavier than all the other quarks. Okay, and so the top, the physics, the top physics, the physics of the top quark, it's really a very important chapter of the particle physics, experimental and theoretical. And so, actually, LHC is producing so many top quarks that you can study the cross-section as a function of center of mass energy, and a differential cross-section. And what you find is that, the results are consistent with what were found already at the Tevatron at Fermilab a few years before the starting of the LHC. And you have also a prediction about the mass of the top. This is a few years old, this plot. There should be another one more recent. But as you could see, we reached now a very precise measurement of the mass of the top quark. Okay. And the latest value, as you could see, is about 172 GeV with this uncertainty. So we have the best mass measurement in the world for the top quark mass. Okay. That's one of the main success of the LHC. But some of the most interesting processes to study are what are called the Drellian production of leptons. This is the Drellian process, which involves the mediator, the production of a Z or a W that then can decay. Okay. And in particular, those processes are they have a very high rate. So they were some of the first measurements done at the LHC, because the Z is a standard candle, so it's considered like a benchmark once you reconstruct it, and it is used also to calibrate your detector. So to calibrate the energy momentum of the particles in a way that the invariant mass of the Z, of the products of the Z decay, matches the value, the nominal value of the mass of the Z measured by previous experiments. Okay. And indeed, you know that, for example, the Z decays in leptons just with a percentage branching fraction of 3% for each lepton flavor, charged lepton flavor, and then 20% in neutrinos, but this is not observable because neutrinos escape from the CMS detector, and the remaining part is in hadrons. But of course, if you want to reconstruct the Z in QQ bar in hadrons, this is much less precise than doing by using leptons. Okay, because leptons can be reconstructed with very high efficiency and very good energy momentum resolution by using the CMS and Atlas experiment. Okay. And what is the topology of the events? And the same for the W. Well, in the case of the W, there is a complication which is related to the neutrino when you have a lepton, a charged lepton. And the energy momentum of the neutrino escapes. So you have to reconstruct it in an indirect way. Okay. What is the topology of those events? Well, in the case of the Z, you have two leptons, which will be very well identified because they generally have large momentum. And then you have the hadronic recoil for the hadronic interaction. And this is the result. So, once CMS and Atlas started to collect the data, after a few months, you see, we were able to reconstruct the Z in E plus E minus. You see the peak of the Z, it's very, very clear. Okay. when we had enough events, the black points are the data, and the other, the distribution comes from the simulation, no? And so we could see the peak of the Z, and here instead we could observe the W also. Well, this is what is called the transverse mass, which is obtained by this equation, and takes into account the fact that the neutrino is lost. And so the only way to reconstruct the energy momentum of the neutrino is in the transverse plane. Why? Because of balancing the energy momentum in the transverse plane, and so I mean the statistics of W and Z was enough to discover again those standard candles. But for example, in the case of muons, we were able to rediscover all the muon resonances. So the low mass resonances, as you could see here, eta, rho, omega, phi, the j psi, the upsilon, the psi prime, and then the z. So these histograms shows you the power of those experiments that essentially were able to discover all the resonances that were discovered in the previous with previous experiments. So essentially all the physics that was discovered in the last 100 years was rediscovered at the LHC in the first period of data taking. So if I give you a sample of data collected by CMS, you can find by yourself those resonances. So those are real. Okay, and I think this is really fascinating, or at least it was for me. But then, is there any other resonance at very high energy? Well, until now, we didn't find any resonance at very high mass. So we were looking for example, at Z prime particles, which are expected in models beyond the standard model, with mass up to few TeV, few tera electron volt, but we didn't find it. Okay, and so the highest dielectron resonance that we know is the Z until now. And we were looking also for other resonances, but we didn't find it. Okay. And the measurement of the cross-section for the Z production and the W production was also very like, along the extrapolation that you could get from the measurements at the previous hadron colliders. So, for example, UA1 and UA2 were the experiments that were used by Carlo Rubbia to discover the W and Z and to measure for the first time the cross-section. And then there were measurements at CDF and D0 at Tevatron, Fermilab in Chicago, and then those by CMS and Atlas. And all of them are compatible with the prediction about the cross-section given by the theory, electron weak. But there are also many other predictions from the quantum electrodynamic, QED. So the electron weak treatment. For example, the production of 2Z and then decaying in 4 leptons. Okay. This final state is very, very clean because you have 4 charged leptons. And you could observe, for example, here is the invariant mass of the 4 lectures, you could see, I mean, the peak here, for example, this is related to 1Z giving 4 lectures, while the other one is of Marshall. And here you have this kind of shoulder related to the on-shell production of the 2Z. This is an electroweak process, so you can compute the cross-section from the theory and compare with the experiment. Okay? And the same for WZ production. Okay? But also, I mean, many other measurements were done in the electroweak sector. So, as a summary of this lecture, which was the yesterday lecture, I mean, here you have a plot of the cross-section measured for all these kind of processes, starting from the W and Z production, and then moving to W plus 1 photon, Z plus 1 photon, WW, WZ, ZZ, and top production, TW single top production, TT bar Z production, and then up to the X region. And we will now move on with the discovery of the Higgs particle, which, as you can see, is, I mean, related to cross-sections which are much lower than what we have been looking at the beginning of the LHC. No? Several order of magnitude less. For example, if you compare the gluon-gluon fusion, you see that there are almost 4 or 5 order of magnitude of less cross-section with respect, for example, of the production of single Z. So the Drellian process that we saw before. Okay. Everything can be computed. So you can compare the prediction from the theory with your experimental measurement. That's something, I mean, it's really amazing because, I mean, you do all your calculation, you study theoretical physics, quantum field theory, and whatever, Feynman diagrams, Feynman rules, and whatever, and then you can test the prediction with your experiment. Okay? We do the same for the Higgs sector of the Standard Model. Okay, so I need to switch to the other file. And so I will briefly go through the history of the discovery of the Higgs boson. Right now we are doing a very precise measurement. And one thing that I want to mention is that when LHC started, the center of mass energy was 7 TeV, then it increased to 8 TeV, and then it increased to 13 TeV, and now it's 13.8. Over all this scan in energies, we always found the Higgs boson in data. So just to confirm you that is not something that could be observed at a given center of mass energy and then maybe it disappears. It's something that really exists in nature. Okay, you need to get convinced that it is not only a prediction of the theory of the Higgs mechanism. It's something that really exists in nature and exists irrespective of the accelerator used, the center of mass used, the selection used, because the signal is very clear, the techniques used, the algorithms and whatever. So it's something that really exists in nature. It's like the Z. Okay. It's a standard candle. Okay, so let's go through the Higgs sector of the Standard Model. Well, you have heard a lot about that from the theoretical point of view. I just want to mention that here is a kind of timeline of the discovery in particle physics, starting from the electron, and then okay, here it's referring to the first experiments by Thomson, essentially, and then X-rays, and then the muon, and then evidence of neutrinos, quarks, gluon, W, Z, top, quark, tau, neutrino tau, and then a Higgs boson. So you see that, we have, in the last 100 years, we had so many discoveries. But the Higgs boson was, for the first time, predicted by those people, Peter Higgs, François Englert, and Brown, in 1964. So it took more than 50 years to discover it. So those people are still alive, Higgs and Englert. Brown died before the discovery, essentially. And they are very old. They are more than 80 years old. And the 4th of July of this year, 15 days ago, they took part to this ceremony for the 10 years of the Higgs discovery in remote. They were not present at CERN. And they really look very old, and they cannot even talk so well and whatever. Okay, but think about what they predicted as theorists in 1964, and then the discovery of what they predicted happened about 10 years ago. And there was also this group, Guralnik, Hagen, and Kibble, that was working in parallel with and independently on with respect to Higgs, Braut, and Englert, and they were also claiming for the discovery, to get the Nobel Prize. Unfortunately, they didn't get the Nobel Prize. Yes.
Actually, you try to mention about the Higgs discovery, Phil Anderson and Alexander Markovich Polyakov were one of the first few people to receive the ideas. So why they are not mentioned?
I'm not aware about that. I know those people were publishing for the first time something about the Higgs boson. Actually, it's only Higgs that mentioned the prediction of a particle, a new particle, while the others were solving the problems of the theoretical problem of the spontaneous symmetry breaking. But it was only Higgs that really pulled out the existence of a particle. Those are the original articles, and it was just Peter Higgs that pointed out the existence of a scalar mass to solve the Higgs, to solve the problem of the gauge invariance of the theory. To preserve it through the spontaneous symmetry breaking. And Englert, Braut, Guralnik, Hagen, and Kibble didn't comment on the existence of this particle. Okay. And Guralnik, Hagen, and Kibble didn't get the Nobel Prize, but they get the EPS prize, so from the European Physics Society. Okay. But they were very unhappy about that because they want to get the Nobel Prize.
But they also get the Scribe Prize in particle physics.
Also. And you have heard a lot about the Higgs mechanism, so I don't go through all the mathematical detail. I mean, you know better than me. I mean, all the details about the degenerate, the degenerate minima, and the fact that you have to choose. I mean, nature choose this minimum as the only one suitable to get all the terms for the mass and couplings of the Higgs boson with the other particle. What I just want to mention is that standard model can predict everything, but not the mass of the Higgs boson. So the mass was a parameter of the theory, together with the other 18 parameters of the standard model, which were essentially the mass of the fermion, the quarks, and whatever. And so, I mean, until the Higgs was discovered, we were looking for Higgs boson of whatever mass, starting from very low mass up to very high mass. Okay. And still now, after we discovered the Higgs boson, we are looking for additional Higgs boson at higher mass. Why? Because in theories like supersymmetry, the minimal supersymmetric standard model, the 2X doublet model, and many others, the prediction is of about 5 Higgs bosons, not just one. And so we are looking for additional Higgs bosons. And that's because in those extensions of the standard model, you don't have just one Higgs doublet, you have 2 Higgs doublet. And so then you could have 5 Higgs bosons, okay? And the standard model allows you to predict the coupling of the Higgs to fermions, the coupling of the Higgs to gauge boson, W and Z, the triple Higgs coupling, and the quartic Higgs coupling. So once the mass of the Higgs boson is measured, you can essentially, have all these numbers. Okay, but the mass was unknown, and so that's why you need the experiment. Okay, that's why the search of the Higgs boson lasted for a long time, because we didn't know the mass, and we had no idea of what could be, because for each kind of interval of mass there were anyway pros and cons. Okay, right now we discovered the Higgs at 100 with a mass of 125 GeV, but there are still some theoretical problems that are raised by the fact that the Higgs is so light. Okay, so not everything converges. As I mentioned yesterday, there are some divergences to the mass of the Higgs boson coming from radiative correction, which are not really absorbed, and they require an unnatural tuning of the theory, of the parameter of the theory to get absorbed. Okay. Or you need additional particles like supersymmetric particles or whatever. So, the path to the discovery of the Higgs boson was quite long. Think about, for example, the LEP electron-positron collider, which was the accelerator that was then replaced by the LHC. So in the tunnel of the LHC before, there was an electron-positron collider, not a proton-proton collider. And they were looking at the Higgs through what is called the Higgs-Strahlung process, which is like a Bremsstrahlung, but with the difference that it's not a photon irradiated by an electron, but it's an Higgs boson irradiated by a Z. That's why it's called Higgs-Strahlung. Okay, and so the Higgs boson was looked through this kind of production process. So this is the Feynman diagram. And at that time, of course, the mass was not known, and so you were looking for the difference hypothesis for the mass. And according to the mass of the Higgs boson, different decay modes are more dominant. Some they could open, some they were closed. Okay. And for different range of mass of the Higgs, you then looked for different final states. So X to gamma gamma, if it was very light, then X to leptons, E mu mu, X to gamma gamma, gluon gluon, and then X to tau tau, C C bar, and then for larger value of the X mass, you could produce on mass shell WW and ZZ. So, as you can imagine, there were an incredible amount of researches and analysis that were performed. But at some point in 2000, the Aleph experiment, which was one of the experiments along the LEP collider, identified some events that could be compatible with the Higgs production. So they measured some, they observed this kind of events, which is compatible, which is an E plus E minus BB bar QQ bar event, which is compatible with the production of an Higgs particle with a mass of 114.3 GeV. So LEP was somehow getting information about the Higgs particle, even if the mass was not exactly what we learned from the LHC. Indeed, there was an excess found by Aleph experiment that was perfectly compatible with the signal for a Higgs particle at 115 GeV. But this signal was just so observed by the Aleph experiment and not by the other experiment. And so really nobody believed on that because just 1 over 4 experiments which were along the LEP collider observed this kind of signal. And you need at least a second experiment that confirms your observation. Otherwise you don't believe. It could be a statistical fluctuation. And indeed it was a statistical fluctuation. Because then we discovered the Higgs with the LHC at 125 GeV. So 10 GeV more than what observed with the LEP collider. And but the search for the Higgs was also done at the Tevatron at Fermilab in a different production mode, because at Tevatron the collider was a proton anti-proton collider, and so the main production mode was still what is called the gluon-gluon fusion, but is the associated production with a Z or a W that really could give the maximum sensitivity at low mass for the Higgs. And again, a lot of searches there, and the day before the announcement of the Higgs discovery at the LHC, Tevatron announced before LHC to have an excess of more than 3 sigma, of about 3 sigma, at around 125 GeV. It was done on purpose, the announcement, before the CERN announcement. Okay, just to claim that Tevatron observed the Higgs boson and not the LHC, which is wrong, because you will see now that CMS and others were observed with 5 sigma significance, the Higgs boson. We have heard about the LHC, so I don't go through all of these slides. I just want to give you some information about the first Z2 mu candidate discovered in March 2010. This is the event display of that candidate when it was observed. And then all the other resonances of the standard model were observed before the Higgs discovery, as we mentioned before. But how the Higgs was produced at the LHC? Well, the main mechanism is what is called gluon-gluon fusion, where you have gluons, a virtual loop of quarks, top quarks, and then the Higgs. This is the most probable production mode for the Higgs boson, with a cross-section of about few picobards. Okay. Still much lower than whatever other cross-section measured at the LHC. Okay. It's a very rare production process. Okay. And then, of course, as I said, we were looking through a mass hypothesis in a very large range, even up to 1 TeV. But the main decay channel that were explored were the Higgs decaying in gamma-gamma and ZZ to 4 charged leptons. Why? Because the photons and the charged leptons are really well measured with the CMS and Atlas detector. So we are quite sure about the uncertainty on the measurement, on the energy and the momentum. And so you could reconstruct the mass of possible resonances very precisely. And as you could see from the diphoton invariant mass, you could get an uncertainty on the mass of the resonance of about 1-2%. And the same for the uncertainty on the resonance from the 4 charged leptons. So all the other decay modes, which maybe are more probable than the X to gamma gamma and the X to ZZ, as you could see here, X to gamma gamma has a branching fraction of 0.23%. with respect to 57% of the X to BB bar. So even if the probability of the Higgs decaying in gamma-gamma and also in ZZ to 4 lepton was very low, but the final state was so clean that you can discriminate the signal from a potential background. While in all the other cases where you have jets, hadrons, neutrinos, and whatever, this could be much more difficult. So, from the experimental point of view, it doesn't matter only the probability that a process, a signal, is produced. But it matters also how this signal could be discriminated from the background. Okay. And with the clear signature of high energy photons and charged leptons, you clearly can reconstruct the mass of the resonance. And this is what has been done. And okay, here there is a description of this analysis, but I just want to give you a historical introduction first. And I want to tell you that in 2011, July 2011, we were very skeptical about the Higgs existence, because we were able to exclude, by using a statistical interpretation of data, a large amount of the mass range. Well, actually, just very small, narrow ranges were not excluded. You see that CMS was able to exclude the Higgs in the mass range between 149 GeV and 2006, and between 300 and 440 GeV. So we were able to exclude the existence of the Higgs over a quite large mass range, and just very narrow windows were left. But what happened? It happened that between in the last year of data taking of the LHC, some candidates, potential candidates for the Higgs production appeared. So were observed. They were not observed before. This was one of the first candidates of 4 muons that was compatible with an Higgs particle with a mass of 145 GeV. It was just the first candidate. Okay. Since the mass was very far from 125 GeV, what we observed, collecting more statistics, this is very likely was a background event from electroweak ZZ production. But it was the first candidate that was compatible with the search for an Higgs particle. Yeah. This another one with a mass of 126 GeV, again a 4 muon candidate. This was a 2e2 mu candidate, 2 electron and 2 muon candidate, again with this mass. And so suddenly this kind of plot of invariant mass of the 4 charged leptons started to be populated by events. And here was the prediction of the Higgs at around 126 GeV. And this region was blind at the beginning. So what does it mean? It means that you don't look at the data in this region until you didn't complete your analysis with the simulated data and with data in the sidebands. This because you don't want to be biased by a possible signal here observed in data. This is what we call a blind analysis. So you don't want to be biased by the fact that that could be a potential signal somewhere. So what you do is you don't look at this region where a potential signal could appear. That's what we did. And suddenly, I mean, we started to see a clustering of events in data, not compatible with the background, what you see here in blue and green, but compatible with a possible signal from the Higgs boson. Then, of course, I mean, to quote a discovery, you need to have a statistical analysis. So you have to quantify your access with respect to the background prediction. And so we use a complicated statistical analysis, and we speak about then a number of sigma, 3 sigma for evidence, and then 5 sigma for discovery. Okay? And CMS pulled out a 3 sigma excess at around 125 GeV. This was a candidate event for the X to gamma gamma, and also you could see an excess around more or less the same value in the invariant mass of the dipole. So this 3 sigma excess here, 3 sigma excess here, gave you a 5 sigma discovery for a new particle at 125 GeV. At that time, we were not sure that that particle was the Higgs particle. We just were sure about the fact that this particle had to be a boson. Okay. And why we were not sure about the fact that it could be an Higgs boson? Because to be sure that it was the real particle predicted by Peter Higgs, you had to measure all the properties, not only the mass, but the couplings and the width and whatever. Okay. And but the 4th of July 2012, CERN announced the discovery of a new particle, and those were the papers quoted by CMS and Atlas for the discovery. And here you could see the Peter Higgs and Francois Englert in the main auditorium at CERN when the discovery was announced. They were invited at that time, even if we were not sure about the fact that really we discovered what they predicted 50 years before. And this is somehow the evolution of the four-charge electron spectrum once more and more data were accumulated. As you can see that, events started to accumulate in this region, where the background was not enough to explain this axis. While in all the other parts, the background in blue was quite matching what you have seen in data. So this kind of axis was then compatible with an Higgs particle with a mass of 126 GeV in this case. And the same for the X2 gamma gamma. You see that once we accumulated data, an axis started to be visible here. Okay. That was the axis at around 125 GeV that was sufficient to claim for a discovery. Okay. And then many other things happened. The first measurement of the mass, the evaluation of the properties, the spin parity of this particle. In particular, all the experimental data confirmed that this particle was a 0 plus particle, so a particle with spin 0 and positive parity, +1. All the other hypotheses of 0 minus, 1 minus, 1 plus, 2 plus, 2 minus, were all disfavored by data for more than 3 sigma. Okay, so that was the first indication that really what we observed, exactly what Peter Higgs and Francois Englert were predicting. Because the Higgs boson from the electro-Higgs spontaneous symmetry breaking came out with 0 plus spin parity. Okay. And that's why they got the Nobel Prize in 2013. Okay. With the explicit mention of the discovery with the Atlas and CMS experiments. Some people here are members of the CMS experiments, and they were involved at that time in the discovery. Okay. This was the plot shown at the ceremony for the Nobel Prize, and I was very happy about this because I was working on this analysis before. What happened then? Well, many measurements were done. The Higgs was discovered also in other channels, decay channels, and I will mention that. For example, the Higgs, we had evidence of the Higgs for the X2 tau tau decay with more than 3 sigma. Okay. And after 2 years of the discovery, this was the picture we had at the LHC. No evidence for any new physics, but confirmation of the prediction of the standard model for the Higgs boson. Then the accelerator was run after 3 years at the center of mass energy of 13 TeV. So we moved from 8 TeV to 13 TeV. And then we looked again at the existence of the Higgs boson, just to confirm that, that particle exists also at higher center of mass energy. It was not an artifact of the analysis itself. And then we come out with the run 2, which ended a couple of years ago, and we are still analyzing the run 2 data. We have plenty of analysis that needs to be completed with the run 2 data, even if just 10 days ago the run 3 started. Okay. And actually the machine, LHC, was giving a peak luminosity which was 2 times better than one expected. So really this machine, this accelerator, was performing so well with respect to the prediction, and even better than what we expected. So it's a really wonderful machine. It's a very precious machine. And then the Higgs was rediscovered with, of course, many data in both the 4-lepton final state, gamma-gamma, but also the couplings started to be measured, the couplings to gauge boson, the couplings to fermions, and also searches for beyond standard model Higgs were performed. I don't know if I have to stop and continue after lunch, or if I can continue for a while.
I think you have 5 minutes.
5 minutes?
Yeah.
Okay, so I will just give some hints about Higgs to BB bar, and then I will continue after lunch, okay? I have plenty of things to do. So, let's think now. We discovered the Higgs in ZZ, in gamma-gamma, but what about all the other channels? Well, I want to measure the Higgs in BB bar because the Higgs in BB bar was exactly the decay chain that was studied at Tevatron before and at LEP before. Why? Because it's the decay with the highest branching ratio with respect to gamma-gamma and ZZ. This has a branching ratio of 58%. So is the decay chain the most probable for the Higgs boson. Okay, but the caveat is that it was much more difficult to observe because, B jets are jets. They are reconstructed with much lower efficiency with respect to photons and charged leptons. And so the background for this kind of search, Higgs to BB bar, the signal over background was much lower than what you could have with 4 charged lepton in the final state. You see, the signal over background ratio was 0.05 in the case of the Higgs to BB bar decay. So with a tiny excess with respect to the background. While in the case of the Higgs to ZZ to 4 leptons, even if the branching fraction was much lower than this one, the signal over background was 2. Okay, so this channel was much less probable than this one, but it was cleaner, with the signal over background much 200 times larger than this one. And that makes the difference. So you could have a very rare process, but very clean in terms of signal to background rejection. X to BB bar was anyway observed, but after many years of data taking. So it was observed recently. Okay, and it was observed once both CMS and Atlas were able to improve the techniques to B-tag the jets. What does it mean? It means that if you have a jet of particles, you want to be sure that that jets come from the hadronization of a B quark. Because if you want to discover Higgs in BB bar, you have to be sure that the jets that you are observing come from the B quark. So it is a B jet. And the B quark and the B meson have the properties that they can they can cross the detector, part of that, and they could give secondary vertices. That's how you can tag a B jet. Okay. And so the technique for B tagging in the latest years used the deep neural network. So machine learning techniques to improve the discrimination between a real B jet against a jet coming from the hadronization of a light quark, UDS, or a gluon. Okay, that was fundamental. So the use of machine learning techniques, in this case a deep neural network, was fundamental to do data analysis for those very complex signal. And for what? I mean, our techniques used before, based on CATs, analysis CATs, were not performing as well as the neural network. Okay, this is just an example, and let me show you what we got once, we subtracted the background from the distribution of the jet invariant mass. So the markers are the data, everything else is background from standard model, the signal from X is the one erected. Once from the data you subtract the contribution of the background, you came out with an axis. It's a very good peak. It's not at 125 GeV, but this is because the mass resolution, once you reconstruct B jets, is not 1%, 2%, it's 10%. Because it's much more difficult to reconstruct the energy momentum of a B jet with respect to a lepton. For a lepton, it's easy. Okay. And so we claimed for a 5 sigma, and so the X in BB bar was observed. Okay. And the same happened also for X to tau tau, for the production of TT bar X. So the production of the X with a pair of top quarks. And again, here we got a 5 sigma observation. Recently also we had studied the decay of the X in CC bar. We are not yet sensitive to that. Why? Because the C quark hadronize and give you D mesons. But the D mesons have a lifetime which is not as long with respect to the B meson. So they are much more difficult to discriminate from light quark jets. That's why we are not sensitive enough to observe the decay of the X in CC bar. Okay. But this will happen. Will happen with the neuron tree, this new data, and with the high luminosity at the LHC. Okay. And finally, let me mention the X2 mu mu, which is the very latest evidence that we got at the LHC last year. So we were, even if the branching ratio of the X decaying in mu mu is very, very small, we were able to observe the X decaying in mu mu with an excess of about 3 sigma, which corresponds to an evidence. That's the first time. Okay. So the X particle then, it was observed in many decay channels. And all the prediction about the couplings of the Higgs with those particles are consistent with the prediction of the standard. Okay. And I think I can stop here, and I will continue after lunch with the couplings. Okay? Any question now? Yes, please.
So, 5 sigma discovery of the Higgs only achieved after long data?
2 channels?
Yeah, the 5 sigma discovery.
At the time of the discovery was only reached with the 2 channels.
After run 1, it was really...
The 2 channels, ZZ and the gamma gamma. But after that, we had also 5 sigma in X tau tau, in TT bar X, X BB bar. Once you get more and more data, you become sensitive also to the other decay chain channel.
Other decay channels, other than the...
Exactly. Exactly.
I have a question about
Yes.
you mentioned decay that goes into F2 and neutrino.
Yes.
Okay. And you said that the momentum of the neutrino is hard to keep track. So we heard about the new result of the mass of the W explosion.
Right.
So it may be this uncertainty of the momentum or
Yes. No,
what changes the new measurement of the W explosion?
okay, you can measure the energy momentum of the neutrino indirectly by using what is called the missing energy. So you balance your energy in the transverse plane. Sorry. But you cannot reconstruct the energy momentum of the neutrino along the z-axis, so along the beam axis. So some parts is missing. Okay, so that gives you uncertainty on the mass of the W. Now you can use several techniques to improve this uncertainty. That's what has been done recently. But still, I mean, the measurement that was quoted seems not to be enough accurate to justify a deviation from the standard model. The problem is that with the neutrinos, you cannot be as precise as for the leptons, because they just escape. Okay, and that's why we have a large uncertainty on the mass. Still very good, but I mean, we are waiting that CMS, for example, pull out the measurement on the mass of the W. Is not yet public because the analysis is very difficult and there are a lot of uncertainties which are not very well under control. Okay. So yes, we have heard about the claim by other experiments about this measurement of the mass of the W, but I think we are not sure about how that measurement is really good and reliable, I would say. Okay, so then we stop here and we continue after lunch, okay?
Yeah.